Welcome everyone. So this is our 31st live stream geometry, and today I'm going to be doing problems from Math Beyond Limits. So it's a summer math program in Poland for advanced high school students throughout Europe. So I'm not sure if it's all of Europe or the countries surrounding Poland, but it has a lot of very tricky problems that they went through. So all the problems I'm going to go over today are just from the year 2017, but maybe in a future session I'll do some of the problems from a different year. So with that, I'm going to share my screen. Hold on just a second. All right, you all see it? All right, so here's the first problem. So we have a triangle ABC. Then we draw the line perpendicular to AC and going through B. And we see where it intersects the circle with diameter AC. So we draw the 2 points. Hold on just a second. So this point and this point. And then we do the same thing on the other side. So clearly this intersection, the foot of the altitude here lies on this circle, and the same with the other side. So let me first finish drawing all of it. But since this is a right angle, it lies on this circle, and since this is a right angle, it lies on this circle. But we draw these 4 points, and what do they call them in the problem? So the circle, the line perpendicular to AC, so X is closer to B than K. So this is X, and this is K, and then this is Y, and this is L, and we want to show that K, Y, and XL intersect on BC. And yeah, these two circles intersect at the foot of the altitude from A. So I guess I'm going to draw that. Let me clear some of the excess in the diagram. And then this point's the orthocenter. And we want to show XY and KL intersect on BC. I thought it was KY and XL. Let me make it better then. So, because it's hard to see where they intersect here. Okay, so something like this. Basically, I guess another way to say it is that BC, XY, and KL concur. That's another way to say it, right? I wonder if it's also true that KY and XL concur on BC. That would be kind of interesting. Yeah, I think probably whatever argument you could use to show that KL and XY concur, you could use to show that KY and XL concur, I bet. All right, so is it radical axis theorem? How should we do this? I wonder if we could use the radical axis theorem. Looks like it, yep. At least I thought. So it looks like KLXY is cyclic. Is there some other quadrilateral that's cyclic? I'm not sure. What if I try drawing the midpoint of BC? It's just a guess. No. So yeah, I want to use the radical axis theorem. It looks like KLXY is cyclic. Is there some other circles that I could use? XY. I wish XYBC was cyclic, but it doesn't look like it's true. XY. Seems like E is the only point I could think of where we could use like the radical axis theorem in a good way. Let's think about this. If this is cyclic, yeah, I feel like I really want to use the radical axis theorem, but I don't know. Maybe that's not the best way to do this. So, I mean, yeah, that's another, I mean, we could show that. I wonder if there's something special about this point right here. If we could show that XYEM is cyclic and LKEM is cyclic, that would solve it. But what is point M? Is there anything special about point M? So I haven't used that these points lie on the circles. So yeah, I could use power of a point to show that XYKL is cyclic, right? Because LF times FY is AF times FE, which is the same as XF times FK. So yeah, by power of a point, we could show XYKL is cyclic. We just have to, if I try that. Yeah, I don't know. I'm not sure what to do here. So yeah, I mean, we know that BIHC is cyclic. I don't know if that really helps. Oh, you know what? I think if we can show that angle XEY is equal to angle LEK, then I think that would solve the problem. Let me check if that's true. So angle XEY is 88.7, and angle LEK, yeah, because if angle XEY is equal to angle KEL, then that means that a spiral similarity takes XEY to LEK, and so that means these two circles would have to concur on BC.
Can you draw LX and
theorem? And that's
can you draw
LX
and Y?
I would bet. Um,
Can you draw
start writing
LX and YK?
Yeah, okay. So I'm actually going to delete these for now, and I'm going to add them back in later. But I think we have enough to essentially do the proof. Hey, Serdar, thanks for hopping on. So I'm going to start writing this up. All right. Just make some room here. Okay. So first I'm going to show LXYK is cyclic. All right. So let F be the orthocenter of triangle ABC. And then so then we have by power of a point, LF times FY is equal to AF times FE, which is equal to KF times FX. And that means that LXYK is cyclic. So that's like kind of the converse of the radical axis theorem. So we could draw that circle. It's probably going to overlap the text, I'm sure. That wasn't so bad. It overlaps it a tiny bit, but all right. And then, well, oh yeah, I want to show that the circumcircles of XCY and LEK meet on BC, but that is, like I said, I think that follows from the fact that angle XCY equals angle LEK. So after proving LX, okay, so by Ricards, we could do it that way too. I think I have let me keep trying my idea though. So actually, is it obvious that if angle XEY equals angle LEK, then they concur on BC? Now I'm actually not so sure if that's obvious. It might, let's see. So if that were true, yeah, I'm actually not so sure if that's obvious, is it? But Serdar, so I think you're saying, okay, so yeah, you basically used Ricards on XYKL. So you're saying if LX and YK meet on BC, then KL and XY meet on BC, is what you're saying, I think. And that's because we know BC is the polar of F with respect to that circle. So yeah. Let's see. I wonder if X, Y, and KL intersect at the point that's cyclic with, I bet that's true. So yeah. So we could, okay, so basically draw the circumcircle of XEY and let it meet BC at a point. And then we could show that that point is collinear with X and L. So, yeah, but we need to show that L, X, and M are collinear and K, Y, and M are collinear, right? I think that's probably just an angle chase, though. So let's see, how do we show L, X, and M are collinear?
If we proved
I guess we could try to show angle XMY is angle L M. So Serdar, do you think you have a solution to, do you think you've solved it? So, okay, so, so I think I could see why BC is the polar of F. But how do you know that L, X, and KY meet on BC? Is that obvious? Because of Ricard. Okay, so so by Ricard on what? On XYKL? Okay, so by Ricard's theorem on XYKL, but how does that, I mean, I would think that would mean that this point and, oh, because the line joining those two has to be the same as BC. Okay, so they actually both meet on, yes. Okay, I got you. All right, so nice. Sorry, I was a little bit slow there. Okay, so okay, so we want to show that BC is the polar of F with respect to this circle. So we could show B lies on the polar of F and C lies on the polar of F. But that's true if and only if, because BX, okay, BXFK is harmonic. So, and that's true. So, why is that true that that's harmonic? Because if we project through A onto the circle, we get AXEC. BY and BL are tangents. So angle BYA is, so is A the center of the circle? I didn't even realize that. BL squared. Okay. So, all right, let's write this up. So angle BLA is 90 degrees. So that implies that BL squared is equal to BI times BA, which is equal to BX times BK. So BL is tangent to the circle LXYK. And similarly for BY. So yeah, this is a really nice application of pole and polar. So Ly is the polar of B. With respect to LXKY or LXYK. And KX is the polar of C. And so that means that LX intersect KY equals F. So that means that BC is the polar of LY intersect KX is equal to F. So, and then if BC is the polar of F, then, so by Ricard's theorem, let me give a name to the intersection. So let KL intersect XY equal N, and XL intersect KY equal N. So I don't think we've used M and N. By Ricard's theorem, Mn is the polar of F. So that means that Mn and BC are the same line. So that means that M equals KL intersect XY lies on BC. That was a really nice idea. I really like that proof. Thanks, Serdar. So I will move on to the next problem. That makes sense to everyone? Oops. So here's a fun problem. So you have a triangle ABC with in center I. See, and we draw the line through I parallel to BC. I feel like that's not super common that we have the line through I parallel to BC. So it intersects AC at E and AB at F. All right. And then we draw the BI and CI, and we let E prime be the reflection of E over BI. Is this right? And then we draw the reflection of F over CI. My bad. And we want to show, yeah, we want to show E prime F prime is tangent to omega. Okay, so this kind of feels like a Poncelet's torism problem to me. Whenever I have something like this, but first let me see what I can do with the diagram, because it's looks a little bit messy. So I guess F prime IF and E prime IE are isosceles. So maybe I could hide BI and CI for now. Well, no, but it's not enough to know they're isosceles. Let me draw this point, and I'll hide the rest of the line. And then let me draw this point and hide the rest of the line. Okay, so
Is the tangency point same with the intersection of in-circle and AI?
So we want to show E prime F prime is tangent. Maybe let's see if we can use Poncelet's Theorem. So, oh no, Serdar, I don't hear you. I guess your microphone's currently off. I think it was just on a second ago.
No, it's on.
But I don't hear you. Let me see. That's weird. I don't know if it's my settings, but you guys can hear me, but I can't hear you. That's unfortunate. Because yeah, I think Dat Feng was trying to speak earlier. And I think Dat Feng, you're trying to speak now. I can see your microphone come off. Oh, hold on just a second. I think I know what's going on. Can you guys start talking again? I think I fixed it.
Do you hear me now?
Yeah, now I hear you. Sorry about that. But glad we fixed it.
I wrote something in chat.
Okay. Hold on just a sec. Is the tangency point the intersection of? It could be. Let's see. No, I don't think so. Doesn't look like it. Yeah, sorry about that. Don't want to silence you guys. You're an important part of this this channel. So, all right. Let's see. So, let me try my Poncelet's Theorem idea just for a second. I'm not sure that it really works, but it could. So if I draw the tangent, whoops. I wonder if this is like the tangency point of the mixed linear in circle. That would be really random, but it almost looks like it. Well, I guess to check that, I feel like I'd be kind of lucky if that were the case. Yeah, no, that's not true. So yeah, I'm not sure how good Poncelet's Theorem is for this problem. Maybe there's a simpler way to do it. Let's see. So is IF parallel to AC? Yeah, so IF is parallel to AC and IE prime is parallel to AB, right? One second, guys, I'll be right back. Yeah, maybe like Serdar was thinking, maybe there's something special about this point here. not sure what it would be. Let me try Poncelet's porism one more time. Wait, that doesn't look like the point that I saw before. Maybe I didn't do it right before. So
Yeah, you did it from H.
that was my problem. So yeah, it looks like this reminds me a lot of a problem from the Peru team selection test, where you take the midpoint of ArcBC and you use Poncelet's porism. So I'm going to try that. So basically, if we let M be the midpoint of ArcBC, it looks like EF prime and MK meet on the circle, and then we could use Poncelet's porism. I'm just going to call it M.
Michael, I have a solution for this.
Oh yeah? All right.
It kind of easy. Well, we claim that F prime is parallel to AC, and IE prime is parallel to AB. Yeah, and IF prime divide IE prime is IF divide IE.
Yeah, because this is isosceles. Yeah. So
yeah.
IFB is isosceles. Yeah. I'm sorry to interrupt you. Sorry.
Yeah, and equal to AB divide AC. So we claim that triangle F prime and E prime is similar to ABC.
Okay.
Yeah, and we let J is the let's IJ is the perpendicular of I to F prime E prime.
Okay.
Yeah, and now we're gonna prove IJ is equal to ID. Just let BC tangent to the interval at D, and we prove that 2 point is equal to IL is equal to IJ.
Okay. So hold on just a sec. So yeah, no, I like that idea a lot. So I am going to delete this stuff. Okay, so
Actually, we can find IJ from trigonometry easily, but I don't know synthetic way. Because we know IF prime and IE prime, and we know the angle E prime IF prime. It's A. It equals to A.
All right. So E prime IF prime. Yeah. So first, I'm just gonna start out writing the proof that this is similar. So yeah, let me just write out a bunch of stuff first, and then I'll continue with what you guys are saying. So EFI and CEI are isosceles. So let me try to make it so that I can type it and we can see the figure at the same time. So, oops, sorry. So, all right. So we have angle FIB equals angle IBC equals angle FBI, and so that implies that FI equals FB, and similarly EI equals EC. EC, and So we can actually say, actually, I'll write this like this. So we have, I'll say FB equals FI equals F prime I. And then similarly, EC equals EI equals E prime I. Okay, so
Okay.
and so yeah, then F prime I over E prime I is AB over AC, and then we can also do an angle chase to show angle F prime I E prime is equal to angle A. So let me just write that out for a sec. So we have F prime I over E prime I is equal to FB over EC, which is equal to AB over AC. And then it's an easy angle chase to show that this is equal to angle A. So I'll do that right now. So we have angle F prime I E prime is equal to 180 minus angle FI F prime minus angle EI E prime. And that's 180 minus angle C minus angle B, which is equal to angle A. And that means that triangle F prime I E prime is similar to triangle ABC. And now I will check the chat. So let's see. IF prime over AB, that's a similarity ratio, is IF over AB, is BF over AB, is equal to R over H. Okay, yeah, so I like it. So so we have IF prime over AB is equal to BF over AB, which is equal to R over, we'll say R over the distance from A to BC. So that means that the distance, so this is the similarity ratio of those two triangles. So I'll actually write it like this. So the distance from I to E prime F prime over the distance from A to BC. There we go. And so that means that the distance from I to E prime F prime is equal to R. And if that's true, that means EF is tangent to the end circle. Or E prime F prime is tangent to omega. All right, nice solution. So now I will move on to the next problem. I'll just say, let me just add one thing for the viewers on YouTube. All right, just gonna say what that notation means. Awesome. I really like this. Yeah, it'll be interesting to see after if there's a solution with Poncelet's porism. But this is probably definitely the easiest solution. All right, so we have a triangle ABC, and we draw the B and C X center. So there's a couple different ways. So I personally like using the in-center X-center lemma to draw but yeah, you don't have to do it this way. So this is just my favorite way to do it. So if I draw these two circles, then these are the X centers right here. So this is IB. And this is IC. All right. Consider a chord PQ. Oh, we already drew the circle of ABC. It's pretty nice. So it's parallel to BC, and it intersects. Okay, that's just to make it non-degenerate. So we want to call this chord PQ. PQ. And suppose BC and AP intersect at R. So we call this point R. Prove that IBQIC plus IBRIC is 180 degrees. All right. Maybe
Actually, R is not on BC.
Yeah, I didn't draw it right. Because it wasn't gray. Now, hopefully that will help. All right. So if I move, maybe that looks a little bit better. Yeah, this is a really random.
Can you delete the other circles for now?
Or this circle?
Yeah.
Okay. Do you want me to draw the X circles?
No need.
Okay. That feels so weird to me, just leaving I out there like that. Hey, Yash, did you mean to just raise your hand? But
no, that was a mistake. Please excuse.
Oh, no worries. Thanks for joining us. I see Hakan also joined. All right. Okay, so do you mind if I draw the X circles? I feel like it's so weird just not having.
It's okay.
Okay. All right, thanks. Let me draw, where's the rays? All right. Okay. Okay, so these are the two X circles. Let me hide this and this. All right.
Can you delete FNG?
Okay. Or if you want, what I could do it like this, just to make. Well, I'm going to hide those later, but for now, there we go. Yeah, there's just too much.
There are 2 points.
Yeah. There we go. Can I check if ICP and IBQ intersect on the circle? Let's see. No, but interesting idea. But basically, whenever we have two angles adding up to 180 like this, it makes me think of, sorry, one sec. It makes me think of trying to find a cyclic quadrilateral. So, yeah, R almost looks like, I don't want R to look like I feel like that looks a little better. Can I check if ICIBPQ is cyclic? Yes. No, it can't be cyclic. Or, well, I guess maybe it could have been, but I feel like the fact that P can be like anywhere makes it unlikely. Or P could be anywhere on the circle. Let's check that the problem is just to see it. So, whoops, sorry. Didn't mean to do that. So if we take that angle 74 degrees and this angle 105.6. So yeah, they add up to 180. It's kind of a weird. Is it worth drawing those angles, or that would just make it messy? Yeah, I'm not going to draw those angles for now. But I wonder if we like reflect R. Like, so yeah, I think it's probably worth drawing this line. If we reflect R over that line, let's think about it. Or we could reflect Q over that line. I'm not sure which one's better, but basically if we reflected R over that line, it almost looks like it lies on the circle, but it doesn't. Then we want to show R prime ICQIB is, oh no, not necessarily. Well, yeah, I think so. Yeah, we want to show that would be cyclic. So, yeah, but maybe it's better to reflect Q over it. And then we could show Q prime. So yeah, we could do it that way too. Yeah, this question feels so random. It looks hard to me. So D is the circumcenter of this cyclic quadrilateral, and E is the circumcenter of this. I don't know. That helps a lot. I think we should move angle IBRIC near P. Okay. How do we do that? Let's see. Maybe I could try drawing the circumcircle of that. Does that pass through this tangency point? I doubt it, but it's worth, yeah, no, it doesn't.
I think it passes through the intersection of AQ and BC.
Ah, interesting. Okay. So yeah, probably just for symmetry reasons, it's probably good to just draw both those points, right? So since we drew R, we could let L be that intersection point. And okay, so
Michael.
Mm-hmm.
I gonna let Q prime is the reflection of Q over IC and IB.
Okay.
Yeah.
Sorry.
Yeah, and so that PAQ prime is
collinear.
Collinear.
Ah.
Yeah.
I like that.
And we need to prove that R, IC, Q prime, and IB is cyclic. Yeah.
And so we could use power of a point, probably.
Maybe, but I use another way to prove that.
Okay.
Okay. So I gonna prove the angle Q prime ICA is equal to Q prime R IB.
Okay.
Okay. Could you draw it so I could be easy to say?
Yeah.
Yeah. Yes. Yeah. So I but Q prime is the reflection of Q, so that the angle Q prime ICA is equal to Q ICA.
Okay.
Yeah. So we're gonna prove the triangle ICAQ and RAIB is similar.
Ah.
Yeah.
And that is similar triangles because AICR. I'm sorry. Go ahead.
Yeah, and but we have we have the angle ICAQ is equal to RAIB.
Mm-hmm.
Yeah. So that we need AIB over AR is equal to RQ over RIC.
Wait, so we want to show
Actually, it's the same with the power of point.
So oh, you're saying it's kind of the same idea as power.
Yeah, it's the same.
Yeah, we need to prove that AQ plus AR is equal to AIC plus AIB.
Okay.
Yeah. But the triangle ABR is similar to AQC.
ABR is similar to AQC, so that's kind of the key idea. And that's not hard to prove just by an angle chase.
Yeah, just by angle chase. So that AR plus AQ is equal to AB plus AC and equal to AIC plus AIB.
And I think you really mean times, right? Not plus, right? But yeah.
Oh, no, yeah. Times, not plus. I'm sorry.
It's all good.
Yeah.
But I like it. That's a really nice idea. So yeah, I'm gonna do it the power of the point way, just because I feel like that might be a little easier than using the angles. So hold on just a sec. All right, so let me start writing it up. That was really fast. All right, so I'm trying to just make room for stuff here. All right. There we go. I think this will give me enough room for the proof. So, okay, so AIB, so let Q prime be the reflection of Q. So first I'll just write out some obvious stuff. So IC A and IB are collinear. And that line, okay, so
Actually, similarity is easy to prove from angle chaining. So
yeah, so
this is again the same thing.
So yeah, and IB is the exterior angle bisector of angle B. So first I'll say Q prime, like Q prime, be the reflection of Q over IA IB. Since IAIB is the exterior angle bisector of angle A, that means that Q prime A and P are collinear. All right. Oops. There we go. So let's see, is that, I think we have to use that PQ as parallel. So yeah, how do we, basically, we want to show that, yeah, I think, yeah, so we still need to show that Q prime A and P are collinear, right? I think it's obvious, but I'm just trying to think how to best write it. So we know that AIB bisects this angle, and yeah, because by symmetry, there's actually one more step. So before I write this, I'm going to say, whoops. So we have angle QAC is equal to angle Q prime AM, but QAC is also equal to angle P prime PAB. So first I'm going to write that. So PQ is parallel to BC, means that arc PB is equal to arc QC, and so then we have by symmetry we have angle QAC is equal to angle Q prime AM, or also say angle PAB is equal to angle QAC, which is equal to angle Q prime AM, and that means that Q prime A and P are collinear. Sorry, I see you guys writing in the chat. And once we know that, it's not that hard of a PowerPoint point, because then we want to show PAB is similar to QAC, the triangles. So we have we want to show angle PBA is equal to angle okay, so we know angle CAQ is PAB, and wait, were those the two triangles, PBA and QAC? I don't think so. There was it was a different pair of triangles, right? Let me check the chat. ICA times AIB, AB times AC is AL. Oh, okay. APB is similar to ACL. Sorry, I know that's what you said earlier. I just got confused. Okay, so we have angle ACL is equal to angle APB, and angle PAB equals angle QAC, and that means that triangle PAB is similar to triangle, or we'll say APB is similar to ACL. And so now we can do all the stuff with the ratios. So we have AP over AC is equal to AB over AL. And AC over AL. Let me rewrite it. So AP, let me write AP over AC equals AB over AL, because then we could use the parallelism, and that's equal to AB over AL. I wanted to use the parallel lines. Is that right? AP over AC.
Oh, no. We just need the triangle ABR is similar to ACQ.
ABR and ACQ. Oh, I was thinking about it the other way, like APB is similar to ACL, but that should also work, right?
Yeah.
Oh, but
Yeah.
we want to do it the other way because that's how the problem stated. Okay.
Yeah, because we need AQ prime.
Yeah.
Yes.
So we have angle AQC is equal to angle ADR, and that angle still works, and so that means triangle ABR is similar to triangle AQC, and now I think it gets a little easier because that means that AR over AC is AB over AQ. Is that right?
Yeah. And so that AR times AQ is equal to AB times AC.
Ah, so it's even easier than I thought. We actually don't even need to use the parallelism again. And once we have that, that means that we have the cyclic quadrilateral, and then that finishes the thaw. So IB and then just one more line to finish off the proof. So we have angle IBR IB plus angle ICQ prime IB is equal to, well, I'll just write it like this. All right. Thanks everyone for your help. This is a nice one. And I'll move on to the next one. So Yash, I think has a solution using complex numbers. All right. So I will, sounds interesting. But I will move on to the next one. All right. So, oh, this one was kind of interesting. So, can you guys all see it? So, we have a triangle ABC, and we draw the feet of the altitudes from B and C. There's no altitude button in GeoGebra, unfortunately, but let's call this HB, and this is HC. All right. And we draw the circumcircle of
This
ABC.
is really nice.
Oh, did you say the problem's nice?
Yeah.
Yeah, it is. And okay, so we draw the line HBHC, and we draw the two tangents to the circle at B and C, and they form, those three lines form a triangle. So I'll try to make it fit on the diagram. And So all right. And they're saying the circumcircle of this triangle is tangent to the circumcircle of ABC. So let me try to make it look a little bit better. I think that looks good. Then I'll draw the circumcircle. And we want to prove their tangent, but I'm just going to draw it. So yeah, that is the problem. I wonder if there's anything special about the tangency point. So it's probably worth drawing. Obviously, EA is a symmedian. So I don't know if labeling the midpoint helps. Let me call that, it's probably better to call this H and call this M. And then we know, like we know we have this, right? And we know that angle MAC is equal to angle BAE by symmedians. Can you let the altitudes cut the circle? Yes. So I'm guessing you mean the big.
Oh, actually, the other one.
Oh, okay. All right.
I think DI, the tangency point, and the tangency point GF are collinear.
Okay, interesting.
They are.
Is IG, so basically IG is parallel to DF.
Can you let AE cut the same circle again?
AE.
Yeah, AE.
Okay, so we have a symmedian, we have a harmonic quadrilateral, ABJC.
We will prove that IJG is similar to DEF.
And IJG is similar to DEF.
Yeah, and then we will prove that DI and GF are concurrent on the circle. Then we are done.
Okay. So if we can show.
I think similarity is easy, but concurrence is not that easy.
Okay, so so could I hide this big circle for now? And basically, if first we want to show they intersect on this circle, right?
Yeah.
Okay.
This is probably Pascal. Yeah.
Pascal's theorem. I think there's a good chance you're right. I wonder if that point's collinear with H and M. Ah, it is. Interesting. So maybe we let HM intersect the circle at a point, and we show that that's collinear with ID, and the same with FG. So I know this point, like where HM intersects the circle, that's like the intersection of the circle with the diameter AH, right? So we know that, like, yeah, so, whoops, I hit a little bit too much. But basically, yeah, let HM cut the circle at point K. So angle AKH is 90. That's a well-known fact. And we want to show DI and K are collinear. And then similarly, FG and K would be collinear. And then by what you were saying, I think that would solve it. And we also know AKHCH. We also have this cyclic quadrilateral. So maybe we could do an angle chase. Yeah, this point D though is not that easy to. Maybe we could use the radical axis theorem, because we have HC is DBFC cyclic?
Actually, J is not needed point, so can you delete J?
Okay.
We will find another point.
So what if we took the point circle K, and then we took this circle AKHCHB and this circle? So, oh no, I wouldn't want the point circle. I'm sorry, the point circle B, and then this circle, and then this circle. So, basically, I want to show the radical axis. Oh, I don't think that would help that much. Is this point? I wonder if DJ is tangent. No.
Actually, I found the proof of the linearity.
Okay.
From Pascal, we know that if Ki intersect Ft at some point D prime, then we know that from Pascal, D prime is on HC HB.
Okay. And you're defining K the same way I did, right?
So it's on AK intersection of AK and BC. I said wrong. Ki will intersect BB, tangent at B. Ki.
So Ki
Yeah.
intersects
Tangent at B at D prime. Let's say it's D prime.
okay.
And from Pascal, we know that D prime is on the line. Can you name the intersection of AK and BC?
Yes, sorry. Second.
We know that D prime is on JHC from Pascal. So we know that D equals to D prime. Because HCAB, AK, and BC are concurrent.
By the radical axis theorem.
Yeah.
Okay. And so by Pascal's AKIC BB. So, all right. So that means that basically D. Okay. So I'm gonna first. Oops. So yeah, I'll call it D prime. Okay. So, 1 second. There we go.
The other point is the point AH cuts the circle.
Do we need that point?
Yeah, we need that point.
This point right here?
Now we will prove that DEF is similar to IDG. Well, D prime EF, IDG. We will prove that they are similar.
What is F?
F is the point on the right.
Oh. I think I erased too much. So
actually, we similarly proved all collinearity. KID prime, KDE, and KGF. After that, just similarity.
okay.
And it's probably angle chasing.
So do you still need the Pascals and the power of a
Yeah,
point?
we need Pascal to prove collinearity. After that, we proved 3 collinearity because they are symmetric.
All right. So yeah, once we show D prime lies on HBHC, then by the same argument, or D prime equals D lies on it, then
Actually, D is not symmetric. F is symmetric, but D is similar. Again, we will use Pascal
okay.
for D.
All right, so I'm gonna hold on just a sec. I'm gonna write this up step by step. So,
well, I realized easier. Harmonic,
okay.
ED, BC are harmonic.
All right, let's pick one. So should I still start out this way?
Yeah, we will prove that from Pascal, Ki, D prime are collinear. After that, we will be proved K, GF are collinear because they are similar.
Okay, KGF, but yeah, are collinear by the same argument. First I'll define, so let the circle A, HC, HD intersect the circle ABC at K. And let KI, so I is not in the problem. So let CHC meet all right, and let KI intersect E. Let KI intersect EB at D prime. All right. Now, so, and let AK intersect BC at J. All right. And so by the radical axis theorem, AK, HBHC, and BC concur at J. All right. And then we could apply Pascal's. So that says, so we're applying Pascal's on AKI BCC. So we have CC, is that the right quadrilateral for D and F? Okay, so AKI CB, I'm sorry, AKI CBB. CBB. So we have BB intersect KI. So BB intersects KI at D prime. And AB intersects IC at HC. and AC intersects. So AC. What's the last one? How do we get HB in that? So AC.
So we know D prime must be on HC HB.
And
D prime is the intersection of KI with the tangent at B.
So yeah, we've defined D prime this way, right?
Yeah,
you're saying we know D prime lies on HCHB by the radical.
From Pascal.
Yeah, so I'm trying to apply Pascal's here. So so how do we use, so we're using Pascal's on this hexagon, right?
Yeah, we have J. It's C, J, and D prime. The other point is J, as Hakan said.
Oh, it's J. I'm sorry. I was saying HB. Okay, so we'll get there, but for now it's AK and BC equals J. Okay. Okay. So D prime, HC, and J are collinear. And we know that HC, so if we combine these two facts, that means that D prime, HC, and HB are collinear. D prime, HC, and HB are collinear. And that implies D prime equals D. Actually, they never really defined D, and I didn't even need to put prime because they never really defined B. But I'm just going to delete all the primes. So all right. So
You should change the diagram too, because there are D and D primes.
yeah. All right. And then similarly, F. So yeah, I didn't even define F, but I'll just say, it's hard to make room here. There we go. So, and then, so I'll just say define F similar to D, but on the other side. And by a similar argument, F, HB, and HC are collinear, and also with D. All right. So all right. And now once we have that, then what was the next step you were saying?
So we know that K, B1, BC is harmonic. So we know that K, D1, and E are collinear.
Okay. So let me call this something else, maybe N. So let AH, so KN and E are collinear. Hold on just a sec. So okay, so you're saying we know KBNC is harmonic. So how do we know KBNC is harmonic? Oh, is that well known that KBNC is harmonic?
Yeah, it's well known. We can do that from the ratios.
Yeah, I think we could just project. So, I mean, basically, we know that JLBC is harmonic, and then if we project through A onto the circle, okay. So I'm going to do it like that. So, BCLJ is harmonic. So. And then if we project through A onto the circle, then KBNC is harmonic. We have KBNC is harmonic. And then that means that KN and E are collinear. All right, I'm sure I'm going to have to make some more in here. But it's okay. All right. And then it almost looks like it passes through HC, but that's not true. Okay, here we go. But now let's see. I want to see point F. Whoops. No.
The similarity, but it's an easy angle chase.
Well, it won't let me show just one column, which is what I want to do. I think it's, there we go.
Michael, did you prove that KDEF are cyclic?
KDEF. Is that true that KDEF is cyclic?
It must be.
It must be.
Interesting. I never proved that.
Yeah, you did.
Actually, similarity is enough, I think, isn't it? Because from homotety, we know that K, I, and G are cyclic. After the homotety, we will know that K, D, E, F are cyclic. So we don't need that.
Yeah. Okay.
Oh yeah, because N would go to E. Yeah, if IG is parallel to DF, then the homophily would have to take point N to point E, I guess, right? Is that what you're saying?
Yeah.
Okay. So we need to show IN is parallel to DE.
Yeah, it is kind of easy to show that IN is parallel to DE. We just need to prove that IN is it's perpendicular to BO, with O is the center of the circumcircle.
Okay. Let me make some room here. All right. Okay. So okay, so the first step, you want to show IG is parallel to FD, right?
IG is parallel to FD is because HC is the middle of IH, and HB is the middle of HG. Yeah.
Nice.
So,
I like it. So
yeah.
By a well-known fact, HC is the midpoint of IH. And HB is the midpoint of GH. And that means that that means that HCHB, I'll just say that implies DF is parallel to IG. Whoops, sorry. So once we show KDEF is cyclic, then it would be solved by homophily, right? But you're saying we don't even need that, right?
Actually, we can use that, or we can prove from angle chasing without using them. It will be the same. We will just use angle chasing.
Yeah, because angle IKG, it's equal to angle IAG, and IAH is twice angle BAC. Yeah, so really it's not too hard to show just using angle chasing that it's cyclic. So so angle IKG equals angle IAG. So that's angle IAH plus.
Actually, we should prove the similarity. Can we do that after proving the cyclicity?
Yeah, we don't have to prove that KDEF is cyclic, Michael.
Okay, I think it's easy enough though, right? Because
yeah,
are you saying there's another way that's even easier?
We just need to prove that IN is parallel to DE.
DE, and then the homophily will finish it. Okay.
Yeah.
And
it is because BI is equal to BH, and BH is equal to BN. Yeah. So that two arc BI is equal to BN.
Yeah, I like it.
So if you call O is the center of the circumcircle.
BN. Yeah. So implies IN is parallel to the tangent.
Yeah.
So that means IN is parallel to DE.
Yeah.
And then similarly, actually that's really all we need. So the homothety at A, I'm sorry, the homothety at K takes KI and G to KDEF. So
Yeah.
homothety at K takes king. I like that. It spells the word king to and that means that I'll say that means that KDEF is cyclic and the circle KING.
Yeah, extension to KDEF.
Yes. Great. Beautiful teamwork here. I love this solution. These are not easy problems, so we got through all of them pretty fast. Yeah, I thought, I think maybe Hakan mentioned, I think this might be the fourth problem, but I will, yeah,
I
so
think
this,
we should solve harder problems.